Hello everybody, welcome to the day 7 video lesson of the MBF3C correspondence course. Yesterday we started to look at probability and we looked at experimental probability and theoretical probability. Again, experimental probability is when you determine the probability after actually doing an experiment, so whether it's rolling the dice 10 times, 30 times, flipping a coin 20 times, you're doing the experiment first and then you're determining the probability based on the results. Theoretical probability is determining the probability before doing an experiment. So it's all about looking at how many possible outcomes do you have and how many of those are actually what you want. Today what we're going to look at is what we call probability simulation. Before we start talking about probability simulations, we're just going to do a recap on what we looked at yesterday. And so with this recap, the letters mathematics are placed in a bag. If one letter is drawn at random, determine the probability that it is, and then we have some options. So first of all, what we need to do is count out how many letters we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters in total. So there are 11 possible outcomes that we can get. And even though some of those letters are the same, there's still those two M's are still two M's that would be in that bag. So they're two separate outcomes. Now we want to determine the probability that the letter is an A. Again, we're determining the probability before we actually do it. So this is what we would call the theoretical probability. There are two A's. Again, there are 11 letters in total. So the theoretical probability is the number of successes over the total number of outcomes. So this gives us 2 out of 11. The probability of it being not a C, now there is one C. If there's only one C and there's 10 letters, there are 10 that are not a C, and so this theoretical probability would be 10 out of 11. A vowel, so that's A, E, I, O, U. We have an A, E, A, and I. There are 4 vowels. Again, out of 11, so the theoretical probability would be 4 out of 11. And M or T is exactly what it sounds like, either an M or a T. Again, there are 4 of those. So there's 4 total. There are 2 M's and 2 T's. So again, the theoretical probability of this would be 4 out of 11. So that's what we looked at yesterday. Now we're gonna again look at continue another thing we looked at yesterday, which is the expected value. Again, the expected value is equal to the number of tries times the theoretical probability of getting what you want. So with T's, the theoretical probability, if we look above, there is 2 T's. So the theoretical probability is 2 out of 11. We're doing this 20 times. So the expected value is equal to the number of times we're doing it, which is 20, times the theoretical probability. Again, we turn that 20 into a fraction, 20 over 1. We do top times top, 20 times 2, which is 40, divided by bottom times bottom, 1 times 11, which is 11. We do 40 divided by 11, which gives us 3.6. Now again, we looked yesterday about the rounding rules. When it's 0.6, we can't, even though it's closer to 4, it's still in the middle, so we can't guarantee that it would most likely be 4. So we say therefore we would expect 3, 4 T's. Again, if it's 0.4, 0.5, or 0.6, we say 3 or 4. If it was below 3.4, we would say 3. Above 3.6, we would say 4. Consonants. Now we could count each consonant up above. We found out that there were 4 vowels. If there's 4 vowels out of 11 letters, there are 7 consonants. A consonant is a letter that's not a vowel. So the theoretical probability would be 7 out of 11. Our expected value is, again, the 20 tries we're doing, times 7 out of 11. 20 times 7 is 140. 1 times 11 is 11. And doing 140 divided by 11 gives us 12.7. Now again, because it's 0.7, which is closer to 12 than in the middle, we round up. So therefore, we would expect 13 consonants. We would expect 13 to show up. If we did this a number of times, we would expect 13 more often than anything else. Now, this is everything that we just did here. We looked at in the last lesson. There are times when we want an experimental probability on something that is just not realistic to do an experiment about, and that's when we do an experiment probability simulation. So for example, if we wanted to know an experimental probability of having a family of 3 boys, it doesn't make sense to ask a woman to get pregnant 3 times just for the sake of doing an experiment and seeing what this is. So instead of doing that, we think of some other ways where the probability of having a boy is the same odd as the simulation that we want to do. Now, the probability of a boy, so one boy, is 1/2 or 50-50. So when we're thinking of everyday objects we could use to simulate this, we need an object with a probability that is also 1/2. So some things we could do: we could flip a coin and have heads represent boys. Again, if heads represent boys, the probability matches. Every time you flip a coin, is this that represents having a kid, and the probability is 1/2. We could use cards and have black represent a boy. Again, the probability of getting a black card is 1/2. You could roll a dice and have even numbers represent a boy. The probability of an even number when you roll a dice is 3/6 or 1/2. Again, the key is the probability of getting a boy is 1/2. We need whatever we pick, we need that probability to also be 1/2. So if we were to, in order to represent a family of 3 children, whatever one we pick, we would do that 3 times. And each time we do it, the probability of getting a boy is 1/2. We would do it 3 times to represent the 3 children in the family. So a simulation is exactly that. It's an event that we use to represent the results of a real life situation when it's impractical to actually perform that situation. An example that we're going to go through, the weather network claims there's a 30% chance it will rain every day during a week. How many days would you expect it to rain over the course of the week? So again, expected value, we're expecting 30% it to rain on 30% of the 7 days. This is our theoretical probability. This is the number of tries. The of represents times. Now again, we can't work with a percent. We need to divide it by 100 to turn it into a decimal. So that's 0.3 times the 7 days, which is equal to 2.1. So therefore, because it's 0.1, we round down, we would expect 2 days of rain. And before I forget, I'm just going to go back up here. Whatever we do, again, we would repeat 3 times for the 3 children. Now, describe in detail how you could use everyday objects to simulate the experimental probability of rain on each day of the week. Again, the theoretical probability of rain is 30%, or 30%, whatever percent you have, that's your probability out of 100. We can divide both sides by the top and bottom by 10, which gives us 3 out of 10. So the theoretical probability of rain is 3 out of 10, which means when we're thinking of an everyday object to use, our everyday object must also have a probability of 3 out of 10. So we need to think of something where there are 10 of them, where we can pick 3 of those to be what we want. Now, what we could do, for example, is use playing cards. If we use cards, there are different ways you can do this. We're going to use 10 cards. Those 10 cards are going to be from the same suit, and they're going to be the Jack, Queen, King, and then Ace, 2, 7. So there's 1, 2, 3, and then 7 more cards gives us 10. We have 3 face cards, and so because there are 3 face cards out of the 10, we could say if a face card is drawn, it rains on that day. And the reason we can do this is because the probability of a face card is equal to, again, there's 3 face cards out of 10 cards in total, so the probability of a face card is 3 out of 10, which matches the probability of it raining on any given day. Now, because we're doing this for a full week, we need to put the card back and repeat the experiment. Again, there's 7 days in a week, so we're going to repeat the experiment 7 times. Now, the key here with that is that we're putting the card back. If you don't put the card back, there aren't 10 cards that you're drawing from anymore. So the probability isn't 3 out of 10 anymore. You always have to put the card back before you do it. Now we're actually going to do that again if you don't have playing cards. First of all, I'm going to set up the experiment. So I'm going to have my trial 1, trial 2, trial 3, and so each of these trials represents a week. I'm going to have day 1, day 2, day 3, day 4, day 5, day 6, and day 7, and then I'm going to have my total number of rains. Now again, each trial represents a week. In each trial there are 7 times that we have to do this, 1 for each day. If you don't have a deck of cards at home, you can use random.org. They have everything that you could possibly need. We're going to choose this playing card shuffler. Now you have to be very careful with how you do it. We said that we're going to have Jack, Queen, King, but and then 1 to 10. So if you want, we can count the check marks. We have 5, 6, 7, 8, 9, 10 cards. We're just going to do this with one of the suits. We're going to draw one card from one deck. The reason we're only doing one card, even though we need to do this 7 times, is if you draw 7 cards, again, they're not putting the card back and shuffling. So each time you draw a card, you're only drawing one card from the choice that you did. Now, what we're going to do is actually click draw the card. The first one we get is the ace. The ace is not a face card, so there's no rain. And we're going to do this 7 times. So we get the ace. We get a 6, which is not a face card. We get a 3, 5, and 7. 3, 5, and 7. Again, none of those are face cards. We need to do it 2 more times. We get a 5, and we get a 3. So 5 and 3. None of those are face cards, which means on that day it was a nice week with no rain. So that's one trial. Now we need to do it again. So we get 7, Jack, Jack, 7, Jack, Jack, 6, 2, 3, ace. 6, 2, 3, ace. Again, the face cards are rain, so no, yes, yes, no, 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 no. In this week we had 2 days of rain. Finally, we're going to do it one more time. We get 5, queen, 2, 5, queen, 2, ace, 4, 7, ace. With this one, so no, yes, no, 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 we got 1 day of rain. Now we said that we would expect 2 days. Up above, we got 2 days once. We got 0 and 1, which are close to 2. So that makes sense. Again, if we did this, say, 10 times, you should expect to see 2 more often than anything else. And then you should expect to see the numbers close to 2 more often than numbers that are really far away from 2. So that's doing the trial. Again, I set it up in a nice table. The key to probability simulations are that whatever the probability of what you're looking for is, so the probability of rain for us was 3 out of 10, we need to pick something with that same probability. Now the last part of this note is probability applications. So this is looking at real world applications of probabilities and analyzing whether or not analyzing those applications and whether those probabilities would carry over. Now, John has taken over kicking field goals for his high school football team. So this is when you kick the ball up between the posts. In practice, he makes 17 out of 25 field goals. The experimental probability of Adam, that should say John, making a field goal on any given try. Again, his experimental probability is exactly that fraction that we see, is 17 out of 25. He made 17 out of the 25 he took. If he kicks 3 field goals in the next game, how many would we expect him to make? His expected value, he's taking 17, or his probability is 17 out of 25. He's taking 3 tries. We need to make that 3 into a fraction. 17 times 3 is 51 out of 25. 51 divided by 25 gives us 2.04. And so we would expect him to make 2 field goals. Now this is going back to what we looked at in that past note, explain how we could use a deck of cards to simulate the situation. We know his probability is 17 out of 25. The simulation must have a probability of 17 out of 25. Now there's nothing nice that no suits have 25 cards. The cards aren't numbered 1 to 25. So what I would do instead is, in order to match the similarity, I would pick 25 cards and I would make 17 of those red, and a red card represents a make. I would make the rest, which is 8, black, and have black cards represent a miss. I would draw a card, record the result, and then put it back. And I would do this 3 times to represent his 3 kicks. Again, the key there is that we put it back, otherwise the probability changes. Now, in terms of a real life situation, that was kind of a real life application, kicking field goals, but we're now going to look at one and we're going to analyze it. So a junior hockey player, which means junior hockey is usually kind of 15 to 20-year-olds play junior hockey, scores 60 goals after taking 200 shots over the course of the season. What percent of his shots did he score? To find a percent, we start with the theoretical probability, which is 60 over 200. We divide it to find out what it is as a decimal. So 60 divided by 200 gives us 0.3. And then we times 0.3 by 100 to get it as a percent. So that gives us 30%. So he scored 30% of his shots. If this pattern continues into professional hockey, so he's gone from junior hockey where he's an amateur into professional hockey like the NHL, and he takes 80 shots in that season, how many would we expect him to score? So we would expect him to score, again, if this pattern continues, 30% of the 80 shots he took. Of means times. We need to turn that percent into a decimal, so we divide by 100. So 0.3 times 80, which gives us 24. So we would expect him to score 24 goals. Now the question is, we want to think about some factors that might affect that. When you go from junior hockey, again, he could have been a 19, 20-year-old in junior hockey, and then he's moving into the NHL where he's playing against 27, 28, 29, 30-year-olds. Pro hockey is the best players in the world. Most people are going to do worse when they play against better players. So our player could have been the oldest in junior hockey, but once he moves to the pros, he could be the youngest in pro hockey. So again, he's playing against better players, he's playing against older players. Because he's playing against better and older players, we wouldn't expect him to do as well. So, based on what we know he's done in the past leagues, we would expect 24 goals, but we would understand if that was under 24 goals because, again, he's playing against better players, he's playing against older players. Being a younger player, he may not play as much because those older players would likely play more. he probably wouldn't be the best player on his team, so he might not play as much. All of these factors are things that would affect our estimate. So again, even though we're saying that we're expecting 24 goals, we would understand if he scored less because of all those factors. So that's kind of a probability application, saying what do we expect him to do, but then analyzing that expectation and giving some reasons why he might not quite match it. Maybe he would do better than it. If you can think of some legitimate reasons, as long as you can argue your point, you're going to get the marks for a question like that. The last thing we're going to look at is what a fair game is. A fair game, when we say game, we mean kind of like a casino game, a gambling game, one where you're betting money. The game is fair if the amount of money you expect to win is equal to the amount of money you would expect to lose. So this game is fair if you do it 10 times, you shouldn't have actually earned any money. If you did it 100 times, whoever you're playing against, you should both win the same amount of money. If the expected value is bigger for one of you than the other, then it's not a fair game. So with this, the total expected value is equal to the expected winnings minus the expected losing. And so to find the expected winnings, that is equal to your expected winnings are the amount that you win times the probability of winning, and then we're subtracting that by the amount that you would lose if you lost times the probability of losing. And again, if this is 0, it is a fair game. So an example, you and a friend are playing a game where you both flip a coin. If the coin lands on the same face, then you win and your friend pays you $2. If the two coins do not have the same face, you lose and you have to pay your friend $2. Now, in order to find out if this is a fair game, we need to find the probability of you winning and the probability of you losing. To do that, we're doing a trial twice. So we're going to make a probability tree. Again, when you flip a coin, you have heads and tails. So this is coin 1. And then we do it again. And this is coin 2. We have heads and tails. Heads and tails. We have our outcomes. The first one is heads, heads. The next one is heads, tails. The next one is tails, heads. And then tails, tails. So you win when both faces are the same. So both are heads or both are tails. There are 4 outcomes in total. You win 2 of those 4 times, or half the time. Your friend wins, and again, you win $2. Your friend wins, or you lose $2 when the 2 faces are different. So heads and tails, or tails and heads. Again, that's 2 out of 4 times, or 1/2. Your expected the total expected value is equal to the amount that you win, which is 2, times the chance of you winning, which is 1/2, minus the amount you lose, which is 2, times the chance of you losing, which is 1/2. Those are the exact same thing. 2 over 1. 2 over 1 gives us 2 over 2 minus 2 over 2. 1 over 1 minus 1 over 1, or 0. What that tells us is this is a fair game. Now, the next one, you're playing a dice game with your friend. If the dice comes up with a 6, your friend will pay you $1. If it comes up 1 to 5, you have to pay your friend $0.25. Is this a fair game? Now again, you win. If you win, you win $1. You win if the dice comes up with a 6. There are 6 numbers on the dice, so you win 1 out of 6 times. You lose, and every time you lose, you're going to lose $0.25 or 25 cents. You lose if it comes up 1 to 5. So those are 5 numbers out of the 6. Now, just because the odds are different doesn't mean it's not a fair game. To find if it's a fair game, you have to find the total expected value. Again, this is the expected winnings. You win $1 1 out of 6 times, minus the expected losings, which is $0.25. That's 5 out of 6 times. So we make that out of 1. That is 1 out of 6 minus 0.25 times 5 minus 1.25 out of 6. Now, because this is different, so 1 minus when the bottom's the same, you just subtract the top, gives us negative 0.25 out of 6. It is not 0, which means it is not fair. You don't necessarily have to find out what it actually is. The key is, it's just you have to find out that it is not 0. So that is not a fair game. The last one, you're playing a game of rock, paper, scissors with your friend. He's so confident he'll beat you. If he wins, you owe him $3. If you win, he will pay you $2. And if you tie, he'll pay you $1. Is this fair? Now, we could make a tree for this, or we could make a table. So across the top is you. I put a Y for you. You could either do rock, paper, or scissors. Your friend could either do rock, paper, or scissors. We have rock and rock, paper rock, scissors rock, rock, paper, 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 scissors, paper, rock, scissors, paper, scissors, and scissors, scissors. Now, just to make this, I'm gonna do your friends in red. So rock, paper, scissors, rock, paper, scissors, rock, paper, scissors. Now, you win. Again, you win $2 when you beat him. You beat him, so let's see. Paper beats rock, and your friend is red, so that's him beating you. So, paper beats rock. We have scissors beats paper, and we have rock beats scissors. So those yellow ones there are when you win. That's 3 out of 9, or 1/3. You win $2. Now you also win $1 when it's a tie. It's a tie, rock, rock, paper, paper, scissors, scissors. That is 3 out of 9, or 1/3. And then you lose, and when you lose $3 when your friend beats you. And so your friend beats you, his rock beats your scissors, his paper beats your rock, his scissors beats your paper. So your friend beats you 3 out of 9 times, or 1/3 of the time. Now the total expected, in this case there are 2 ways of winning, so we need to include both ways. You win $2 1/3 of the time. If you're winning the money, it's a plus, so you win, which is why it's a plus, $1 1/3 of the time. If you're losing the money, it's a minus. So you lose $3 a third of the time. This gives us, if we make all of those whole numbers over 1, 2 times 1 is 2 over 3, plus 1 times 1 is 1 over 3, minus 3 times 1 is 3 over 3. 2 plus, again, because the bottoms are the same, the bottom stays 3, and we just add or subtract the tops. 2 plus 1 is 3, minus 3 gives us 0. 0 out of 3 is 0, and because it's 0, it is a fair game. Now, this last little bit you won't be tested on, but it's just a little bit of facts about casinos. Casino games are meant to be unfair. A casino would never have a game in it where they are there's a 50-50 chance of them making money or losing money, or where they're expected to lose money. Casinos are all about them making a profit. So the games are made to be unfair. It is possible, because of the way the games work, for players to make a lot of money, and casinos usually want that to happen. But most of the casino games, for every dollar that somebody plays, they're only expected to get between 90 and 95 cents back, which means that for every dollar that someone spends, the casino essentially makes on average between 10 and 5 cents. So just because someone wins a lot of money at casino, it doesn't mean that game is one where they could win all that money. The casino games are designed for, over the long run, for the casino to not lose money. Now again, the homework's been posted throughout the note. With this day 7, there's just an assignment. You'll see that in the assignments page. Again, for that assignment, you will have to do a probability simulation. If you don't have dice or cards or whatever you decide to use for that simulation at home, I would recommend using cards, but if you don't have them, you can always go to random.org. Again, just as a hint, when you're using the cards, make sure that you only draw one card from one deck, and you keep repeating it over and over. That puts the card back in and keeps the probability the same. Now, you still only get one submission with the assignment, so before you submit it, please make sure that it is done to the best of your ability and completely filled out. Good luck on the assignment.